The final project I worked on was to adapt the heuristic introduced in the paper Reviving Partial Order Planning for the original POP algorithm, which was implemented in Project 1. Partial order planning, or POP, generates flexible plans but struggles with scalability when actions have ungrounded variables. Repop's heuristic improves the efficiency of POP by using a planning graph, but it requires grounded subgoals, which is a mismatch with POP's partial grounding. This project bridges the gap by introducing a dynamic grounding procedure that unifies open conditions, which are partially grounded, with literals in the planning graph, which are fully grounded. Repop estimates the effort to resolve subgoals, or open condition flaws, through the function cost of S. This cost is computed recursively from planning graph levels, and it requires all literals in the subgoals to have grounded variables, because the planning graph is fully grounded. However, POP's open preconditions may be ungrounded during its search for plans. In that case, open preconditions may contain variables that could be substituted into any possible constant. This challenge is solved by treating the planning graph not just as a source for calculating the heuristic, but also as a source for unification for variable binding. This is how the grounding algorithm works. The algorithm starts from a set of preconditions from the current open condition flaws, a set of current bindings for variables, and the planning graph produced by GraphPlan. For each ungrounded open precondition in the open condition set, the planning graph is traversed in search of literals that could unify with it. If some literal is found, then the current bindings are updated with new bindings that support the unification. These bindings will propagate recursively to support the other open conditions. This process guarantees that if the algorithm arrives at a set of bindings at the end, where the set of ungrounded open conditions is empty, the bindings are sure to be able to convert the input preconditions into a valid set of grounded preconditions. The drawback of such an exhaustive approach is its computational cost, where the time consumption explodes as the planning graph has more levels and more literals in it. To mitigate this, the algorithm implements early termination by stopping after a preset limited number of valid groundings. In practice, I stop at the first set of valid bindings found because I find that the neighboring groundings yield similar cost values. Now, with grounded subgoals, the repop heuristic is implemented as described in the paper. The procedure is, first identify the subgoal PS at the level of the highest of any subgoal, and then recursively estimate the cost from actions that achieve it, minus the actions it achieves. It is observed that the recursive cost estimation also quickly becomes time-consuming, especially in larger planning graphs, when the graph has more than a few levels in the depth. This is because in the step that finds the highest level subgoal PS, there could be multiple candidates all in the same level. The only operation in the algorithm that removes literals is the part where effects of the producer of PS are removed. But that does not cause all literals in that level to be removed. As a result, the algorithm could stay on one level for multiple recursions before moving down to a lower level. This increases the time consumption, especially with larger planning graphs and many subgoals. After the cost function is calculated, partial plans are ranked using this evaluation function. For the partial plan P, f of P equals the number of current steps in P plus a weight-adjusted cost, which is the cost of the subgoal set S. Open conditions with minimal heuristic values are prioritized. The default weight W equals 5. This is implemented, but it does not achieve the best results. In my experiments, I find that a variant evaluation function with an additional exponential term helps improve the performance of the heuristic. In the integration stage, the grounding procedure and the heuristic calculation procedure are invoked in appropriate places in the POP algorithm. At the very beginning, the GraphPlan planning graph is initialized and extended so as to support unifications in the grounding, as well as cost estimation for the heuristic. A new heuristic needs to be calculated when we fix an open precondition flaw, because the number of open preconditions will then change. This is when the grounding algorithm is called, and the new heuristic is calculated afterward. This heuristic is then associated with the newly generated plan space node, which fixes the open condition flaw. New plan space nodes are also generated when threatened causal link flaws are fixed, but in such cases, the new node inherits their parent's heuristic, because the number of open precondition flaws does not change. The evaluation of the repop heuristic is performed on the same benchmark dataset used in previous class projects. The repop implementation with the default evaluation function solves 19 out of 26 problems, which improves on the pre-provided pop algorithm. And using the adjusted evaluation function with the additional exponential term, the repop heuristic slightly outperforms my implementation in Project 1. Here is a detailed comparison on the benchmark dataset. In each table, from left to right, are the adjusted repop heuristic, the default repop heuristic, the pop implementation in my Project 1, and the pre-provided pop algorithm. The default repop heuristic does not solve some of the more complex cargo delivery problems, but these are solved using the adjusted plan ranking function. Also, the updated function improves on the last deliver return problem, reducing 2 steps from my Project 1 implementation. Here is a comparison of computation and time cost of pop using different heuristics. Node generation performed similarly to node visited, so that table is not listed here. It can be observed that for problems whose solutions require more than a few steps, the computational requirement increases quickly for repop. The default repop does not solve some of the more complex problems because node limitations are reached. The modified repop solves them, but with generally high node visits and time consumption. I believe that the quick increase of the time cost with larger problems for repop is due to the increase of the plan graph size, which then slows down both the grounding and heuristic calculation, which are recursive. In conclusion, this project achieves the goal of adapting the repop heuristic for the pop algorithm. A dynamic grounding algorithm is developed to support the fully graph-based heuristic. The plan ranking function is also adjusted, which makes the repop heuristic slightly outperform my previous project in terms of total plan length. However, that comes at the cost of more node generation, visit, and time consumption.